Alrighty, so we are going to do the second part of reinforcement learning. Um, you can hear the whole family snoring. Anyways, um, is my audio mixer good? I think so. Yeah, perfect. So, just go channel. Okay. Oh, not this one. I believe we read till page 10. We read till page 10. Let me just go back to this different project. I'm not sure where it is. Oh, here it is. Yeah. This is AI Decide. Yeah. Hopefully we can get through 20 pages or something. We were right about to read Tic-Tac-Toe. Can just move this here. Yeah, perfect. Alright. Tic-Tac-Toe. It should be around here. Alright. So last time we went through what are the four main things of reinforcement learning. One is your policy, two is reward, three is your value function, four is your modeling. And you basically want a good model, and you have to set up a good value function and figure out the value function. That's a very important thing. Then you want to have modeling, which is the planning part of everything. You want to have planning. Alright, an extended example, tic-tac-toe. To illustrate the general idea of reinforcement learning and contrast it with other approaches, we next consider a single example in more detail. Consider the familiar child's game of tic-tac-toe. I just slept for 4 hours. Two players take turns playing on a 3x3 board. One player plays X's, another O's, until one player wins by placing 3 markers in a row horizontally, vertically, or diagonally, as the X player has in this game. If the board fills up with neither player getting 3 in a row, the game is a draw because the skilled player can play so as never to lose. Let us assume that we are playing against an imperfect player, one whose play is sometimes incorrect and allows us to win. For the moment, in fact, let us consider draws and losses to be equally bad for us. How might we construct a play that will find the imperfections in its opponent's play and learn to maximize its chances of winning? Although this is a simple problem, it cannot readily be solved in a satisfactory way through classical techniques. For example, the classical minimax solution from game theory is not correct here because it assumes a particular way of playing by the opponent. For example, a minimax player would never reach a game state from which he could lose, even if in fact it always won from that state because of incorrect play by the opponent. Classical optimization methods for sequential decision problems such as dynamic programming can compute an optimal solution for any opponent, but requires an input a complete specification of that opponent, including the probabilities with which the opponent makes each move in each board state. Let us assume that this information is not available a priori for this problem, as it is not for the vast majority of problems of practical interest. On the other hand, such information can be estimated from experience. In this case, by playing many games against the opponent, about the best one about the best one can do on this problem is first to learn a model of the opponent's behavior up to some level of confidence and then apply dynamic programming to compute an optimal solution given the approximate opponent model. In the end, this is not that different from some of the reinforcement learning methods we examine later in this book. An evolutionary method applied to this problem would directly search the space of possible policies for one with a high probability of winning against the opponent. Here, a policy is a rule that tells the player what move to make for every state of the game, every possible configuration of X's and O's on the 3x3 board. For each policy considered, an estimate of its winning probability would be obtained by playing some number of games against the opponent. This evaluation would then direct which policy or policies were considered next. A typical evolution method would hill climb in policy space, successively generating and evaluating policies in an attempt to obtain incremental improvements, or perhaps a genetic style algorithm would be used that would maintain and evaluate a population of policies. Literally hundreds of different optimization methods could be applied. Here's how the tic-tac-toe problem would be approached with a method making use of a value function. First, we set up a table of numbers, one for each possible state of the game. Each number will be at least estimate of the probability of our winning from that state. We treat this estimate as the state's value, and the whole table is the learned value function. State A has higher value than state B, or is considered better than state B if the current estimate of the probability of winning from A is higher than it is from B. So starting position, opponents move, our move, opponents move, our move, and just keep going, I believe. Interesting. So it's kind of, if you want to think about it, the way we should work is that we play such a game that we assume our player will play their best, such that if they play some inconsistency, not some suboptimal move, then we can exploit that. Alright, let's just write that. Backgammon, right? So let's just make this bigger a little bit. We want to play a game such that we know what the good moves are and plan for a perfect match and exploit suboptimals, right? Okay. Figure 1, a sequence of tic-tac-toe moves. The solid lines represent the moves taken during game. The dashed lines represent moves that I need to blow my nose. Excuse me for that. Consider but did not make. Our second move was an exploratory move, meaning that it was taken even though another sibling move, the one leading to E prime, was ranked higher. Exploratory moves do not result in any learning, but each of our other moves does, causing backups as suggested by the curved arrows and detailed in the text. Assuming we always play x's, then for all states with 3 x's in a row, the probability of winning is 1. Because we have already won. Similarly, for all states with 3 O's in a row, or that are filled up, the correct probability is 0. As we cannot win from them, we set the initial values of all the other states to 0.5, representing a guess that we have a 50% chance of winning. We play many games against the opponent. To select our moves, we examine the states that will result from each of our possible moves, one for each blank space on the board, and look up their current values in the table. Most of the time we move greedily, selecting the move that leads to the state with greatest value, that is with the highest estimated probability of winning. Excuse me for that again. Most of the time we move greedily, selecting the moves that leads to the state with greatest value, that is with the greatest estimated probability of winning. Occasionally, however, we select randomly from among the other moves instead. These are called exploratory moves because they cause us to experience the states that we might otherwise never use. A sequence of moves made and considered during a game can be diagrammed as in figure 1.1. Alright. While we are playing, we change the values of the states in which we find ourselves during the game. We attempt to make them more accurate estimates of the probabilities of winning. To do this, we back up the value of the state after each greedy move to the state before the move. As suggested by the arrows in figure 1.1, more precisely, the current value of the earlier state is adjusted to be just came a thought. Have a matrix that has values for rewards regarding the time and probably have rewards that are not changing anymore. Okay, so we can have the reward system changing in 2 ways probably. One based on position. We can have the rewards changing based on the position. Well, time doesn't matter. Time means the number of steps that are taken right now, and time, basically, the number of steps taken as of now. Okay, that's good enough. To do this, we back up the value of this state after each greedy move to the state before the move. As suggested by the arrows in figure 1.1, more precisely, the current value of the earliest state is adjusted to be closer to the value of the later state. This can be done by moving the earlier state's value a fraction of the way toward the value of the later state. If we let S denote the state before the greedy move, the S prime this state after the move, then the update to the estimated value of S denoted Vs can be written as that where a is a small positive fraction called step size parameter which influence the rate of learning. Okay, so this is for the second video, so let's just compartmentalize it, whatever you call it. Alpha is 0. Yeah, I'm also trying to have this in the standard form so others can understand it. So your rate of learning. More precise, the current value of the earlier state is adjusted to be closer to the value of the later state. This can be done by moving the earlier state's value a fraction of the way toward the value of the later state. If you let S denote the state before the greedy move, the S prime the state after the move, then the update to that. This update rule is an example of a temporal difference learning method, so called because its changes are based on a difference. What was V again? We're on page 13, I believe. So that's your value function. I mean, it didn't say that, but V for value. I'll take that. I'll take that. Sure. The method described above performs quite well on this task. For example, if the step size parameter is reduced properly over time, this method converges for any fixed opponent to the true probabilities of winning from each state given optimal play by our player. Furthermore, the moves then taken, except on exploratory moves, are in fact the optimal moves against the opponent. In other words, the method converges to an optimal policy for playing the game. If the step size parameter is not reduced all the way to 0 over time, then this play also plays well against opponents that slowly change their way of playing. This example illustrates the differences between evolutionary methods and the methods that learn value functions. We need to learn I need water. Value function. Very unprepared today. Learner where are we? We passed the law. Learn function. Why are we on page 89? Oh, God. I hate this. This comes all from not being prepared. Oh. Anyways, this is playing with me either. Also, the frequency of wins gives an unbiased estimate of the probability of with that policy and can be used to direct the next policy selection. But each policy change is made only after many games, and only the final outcome of each game is used. What happens during the games is ignored. For example, if the player wins, then all of its behavior in the game is given credit, independently of how specific moves might have been critical to the win. Credit is even given to moves that never occurred. Value function methods, in contrast, allow individual states to be evaluated. In the end, evolutionary and value function methods both search the space of policies, but learning a value function takes advantage of information available during the course of play. This simple example illustrates some of the key features of reinforcement learning methods. First, there is the emphasis on learning while interacting with an environment. In this case, with an opponent player. Second, there is a clear goal, and correct behavior requires planning or foresight that takes into account delayed effects of one's choice. I like the vocabulary here. Delayed effects of a choice. Plan for results. With an environment that account delayed effects of one's choice. For example, the simple reinforcement learning player would learn to set up multi-move traps for a short-sighted opponent. It is a striking feature of the reinforcement learning solution that it can achieve the effects of planning and look ahead without using a model of the opponent, and without conducting an explicit search over possible sequences of future states and actions. So basically, you don't need to know your opponent, you just make a good choice regardless. That's how it should be. Well, this example yeah, your intuition is the other way, right? To know the opponent. But you should do what's good regardless of the opponent. Alright. While this example illustrates some of the key features of reinforcement learning, it is so simple that it might give the impression that reinforcement learning is more limited than it really is. Although tic-tac-toe is a two-person game, reinforcement learning also applies in the case in which there is no external adversary, that is, in case of a game against nature. Reinforcement learning also is not restricted to problems in which behavior breaks down in separate episodes, like the separate games of tic-tac-toe. With rewards only at the end of each episode, it is just as applicable when behavior continues indefinitely, when rewards of various magnitudes can be received at any time. Reinforcement learning is also applicable to problems that do not even break down into discrete time steps, like the play of tic-tac-toe. The general principles apply to continuous time problems as well, although the theory gets more complicated and we omitted from this introductory treatment. Tic-tac-toe has a relatively small finite state set, whereas reinforcement learning can be used when the state is very large or even infinite. For example, Gary Tesaro, um, years 1992 and 1995, combined the algorithm described above with an artificial neural network to learn to play backgammon. Alright, which has approximately 10 to 20 states. With this many states, it is impossible ever to experience more than a small fraction of them. Tesaro's program learned to play far better than any previous game and now plays at the level of the best world's best human players. See chapter 15. The neural network provides the program with the ability to generalize from its experience. Such a cliche, but let's just write it. Maybe we need to not write it there. I don't know. Because we're gonna run out of space later. I don't know. So great minds existed before me, apparently. The neural network provides the program with the ability to generalize from its experience, so that in new states it selects moves based on information saved from similar states. The guy's just me. Is that play moves? Well, I'm not gonna look at what he did, but probably I should. Play moves from past experiences. I kind of see that point. I don't know if this works still. This should work. You guys like that, didn't you? Okay. And then do this. Oh. So yeah, let's imagine, where are we? We're supposed to choose that. This is our backgammon board. We have 6. Yeah, it's good enough. Alright, so we can change color. That would be appreciated. How do I change color? How do I change color? Oh yeah. Alright. So in backgammon, you start with 3 here, 5 there, 5 up here, 2 up here, and oh. Let's go with blue. The setup is not working. That's 5, that's 3. And we started 2 here. Alright, so now you might think that we can maybe generalize some positions, right? So like the beginning of the games, I can just go back to my eraser. So how I would split these is 1. Beginning, middle game, which is probably, this is where we can generalize. Is the tactical part. In game, probably generous. Alright, enough for now. How well a reinforcement learning system can work in problems with such large state sets is intimately tied to how appropriately it can generalize from past experience. It is in this role that we have the greatest need for supervised learning methods with reinforcement learning. Neural networks are not the only or necessarily the best way to do this. Okay. In this tic-tac-toe example, learning started with no prior knowledge beyond the rules of the game, but reinforcement learning by no means entails a tabula rasa view of learning and intelligence. On the contrary, prior information can be incorporated into reinforcement learning in a variety of ways that can be critical for effective learning. We also had access to the true state in the tic-tac-toe example, whereas reinforcement learning can also be applied when part of the state is hidden, or when different states appear to the learner to be the same. That case, however, is substantially more difficult. Whereas can be applied when part of the state is hidden, or when different states appear to the learner to be the same. So I'm thinking that's more game theory stuff. That's how I feel about it. Finally, the tic-tac-toe player was able to look ahead and know the states that would result from each of its possible moves. To do this, it had to have a model for the game that allowed it to think about how its environment would change in response to moves that it might never make. Many problems are like this, but in others, even a short-term method model of the effects of actions is lacking. Reinforcement learning can be applied in either case. No model is required, but models can easily be used if they are available or can be learned. On the other hand, there are reinforcement learning methods that do not need any kind of environment model at all. Model-free systems cannot even think about how their environments will change in response to single action. Tic-tac-toe player is model-free in this sense with respect to its opponent. It has no model of its opponent of any kind. Because models have to be reasonably accurate to be useful, model-free methods can have advantages over more complex methods when the real bottleneck in solving a problem is the difficulty of constructing a sufficiently accurate environment of environment model. Model-free methods are also important building blocks for model-based methods. In this book, we devote several chapters to model-free methods before we discuss how they can be used as components of more complex model-based methods. Model-free creates model-full methods. Yes. But reinforcement learning can be used at both high and low levels in the system. Although the tic-tac-toe player learned only about the basic moves of the game, nothing prevents reinforcement learning from working at higher levels where each of the actions may itself be the application of a possible elaborate problem-solving method. In hierarchical learning systems, the reinforcement learning can work simultaneously on several levels. Reinforcement learning is a computational approach to understanding and automating goal-directed learning and decision-making. It is distinguished from other computational approaches by its emphasis on learning by an agent from direct interaction with its environment without relying on exemplary supervision or complete models of the environment. In our opinion, reinforcement learning is the first field to seriously address the computational issues that arise when learning from interaction with an environment in order to achieve long-term goals. Reinforcement learning uses a formal framework defining the interaction between a learning agent and its environment in terms of states, actions, and rewards. This framework is intended to be a simple way of representing essential features of the artificial intelligence problems. These features include a sense of cause and effect, a sense of uncertainty and non-determinism, and the existence of explicit goals. The concept of value and value function are the key features of most of the reinforcement learning methods that we consider in this book. We take the position that value functions are important for efficient search in the space of policy. The use of value function distinguishes reinforcement learning methods from evolutionary methods that search directly in policy space guided by scalar evaluations of entire policies. Alright, we have a whole history. Should we read it? Yeah, you know what? Why not? Puts us in the stream. The history of reinforcement learning has two main threads, both long and rich, that were pursued independently before intertwining in modern reinforcement learning. One thread concerns learning by trial and error that started in the psychology of animal learning. This thread runs through some of the earliest work in artificial intelligence and led to the revival of reinforcement learning in the early 1980s. The other thread the other thread concerns the problem of optimal control and switching using value functions and dynamic programming. For the most part, this thread did not involve learning. Although the two threads have been largely independent, the exceptions revolve around a third, less distinct thread concerning temporal difference methods, such as used in the tic-tac-toe example in this chapter. All three threads came together in the late 1980s to produce the modern field of reinforcement learning as we presented in this book. The thread focused on trial and error learning is the one with which we are most familiar and about which we have the most to say in this brief history. Before doing that, however, we briefly discuss the optimal control thread. The term optimal control came into use in the late 1950s to describe the problem of designing a controller to minimize a measure of a dynamical system's behavior over time. One of the approaches to this problem was developed in the mid 1950s by Richard Bellman and others through extending a 19th century theory of Hamilton and Jacobi. This approach uses the concept of a dynamical system's state and a value function or optimal return function to define a functional equation, now often called the Bellman equation. All right. Why have I heard about that? The class of methods for solving optimal control problems by solving this equation came to be known as dynamic programming. Bellman 1957a. Bellman 1957b also introduced the discrete stochastic version of the optimal control problem known as Markovian decision process (MDPs). And Ronald Howard 1960 devised the policy iteration method for MDPs. All of these are essential elements underlying the theory and algorithms of modern reinforcement learning. Dynamic programming is widely considered the only feasible way of solving general stochastic optimal control problems. It suffers from what Bellman called the curse of dimensionality, meaning that its computational requirements grow exponentially with the number of state variables, but it is still far more efficient and more widely applicable than any other general method. Dynamic programming has been extensively what was MDP? Markovian decision processes. Surveyed by Lovejoy, many applications surveyed by White 1985, 1988, 1993, approximation methods surveyed by Ross 1996, and asynchronous methods Bertsekas 1982, 1983. Many excellent modern treatments of dynamic programming are available. Bertsekas 1995, Puterman 1994. That and Bryson 1996 provides an authoritative history of optimal control. Connections between optimal control is a branch of control theory that deals with finding a control for a dynamical system over a period of time such that an objective function is optimized. has numerous applications in science and engineering and operations research. For example, the dynamical system might be a spacecraft with controls corresponding to rocket thrusters, and the objective might be to reach the moon with minimal fuel expenditure. Or the dynamical system could be a nation's economy, and the objective to minimize unemployment. Alright, this is the math. Not sure. Optimal control deals with the problem of finding a control law for a given system such that a certain optimality criterion is achieved. A control problem includes a cost function that is a function of a state and control variables. An optimal control is a set of differential equations describing the paths of the control variables that minimize the cost. The optimal control can be derived using Pontryagin's maximum principle, a necessary condition also known as Pontryagin's minimum principle or simply Pontryagin's principle. Alright, let's just get through with this paragraph and go back. We begin with a simple example. Consider a car traveling in a straight line on a hilly road. The question is, how should the driver press the accelerator pedal in order to minimize the total traveling time? In this example, the term control law refers specifically to the way in which the driver presses the accelerator and shifts the gear. The system consists of both the car and the road, and the optimality criterion is the minimization of the total traveling time. Control problems usually include ancillary constraints. For example, the amount of available fuel might be limited. The accelerator pedal cannot be pushed through the floor of the car, speed limits, etc. Alright, so we get to some math here, which unfortunately I'm not sharp enough right now to get them. But control theory, optimal control. Alright, okay. You can't be sure about what accounted for this separation, but its main cause was likely the separation between the principles involved and their different goals. Also contributing may have been the prevalent view of dynamic programming, of an offline computation depending essentially on accurate system models and analytic solutions to the Bellman equation. Further, the simplest form of dynamic programming is a computation that proceeds backwards in time, making it difficult to see how it could be involved in a learning process that must proceed in a forward direction. Perhaps the first to connect optimal control and dynamic programming with learning was Paul Verbus, who proposed an approximate approach to dynamic programming that he called heuristic dynamic programming. He later argued for the need for greater interrelation of dynamic programming and learning methods and its relevance to understanding neural and cognitive mechanisms. For us, the full integration of dynamic programming methods with online learning did not occur until the work of Chris Watkins in 1989, whose treatment of reinforcement learning using the MDP formalism has been widely adopted. Since then, these relationships have been extensively developed by many researchers, most particularly by Dimitri Bertsekis and John Tsitsikelis, who coined the term neurodynamic programming to refer to the combination of dynamic programming and neural networks. Another term currently in use is approximate dynamic programming. These various approaches emphasize different aspects of the subject, but they all share with reinforcement learning an interest in circumventing the classical shortcomings of dynamic programming. Uh, in this book, we consider all of the work in optimal control also to be, in a sense, work in reinforcement learning. We define a reinforcement learning method as any effective way of solving reinforcement learning problems, and it is now clear that these problems are closely related to optimal control problems, particularly stochastic optimal control problems, such as those formulated as Markov decision processes. Accordingly, we must consider the solution methods of optimal control, such as dynamic programming, also to be reinforcement learning methods, because almost all of the conventional methods require complete knowledge of the system to be controlled. It feels a little unnatural to say that they are part of reinforcement learning. On the other hand, many dynamic programming algorithms are incremental and iterative. Like learning methods, they gradually reach the correct answer through excessive approximations. As we show in the rest of this book, these similarities are far more than superficial. Than theories and solution methods for these cases of complete and incomplete knowledge are so closely related that we feel they must be considered together as part of the same subject matter. Let us return to the other major thread leading to the modern field of reinforcement learning that centered on the idea of trial and error learning. We only touch on the major points of contact here, taking up this topic in more detail in chapter that, according to American psychologist R.S. Woodworth, the idea of trial and error learning goes as far as back as the 1850s to Alexander Bain's discussion of learning by groping and experiment, and more explicitly to the British ethologist and psychologist Conway Lloyd Morgan's 1894 use of the term to describe his observation of animal behavior. Perhaps the first to succinctly express the essence of trial and error as a principle of learning was Edward Thorndike. Of several responses made to the same situation, those which are accompanied or closely followed by satisfaction to the animal will, other things being equal, be more firmly connected with the situation so that when it recurs, they will be more likely to recur. Those which are accompanied or closely followed by discomfort to the animal will, other things being equal, have their connections with the situation weakened so that when it recurs, they will be less likely to occur. The greater the satisfaction or discomfort, the greater the strength from a weakening of the bond. Alright, Thorndike called this the law of effect because it describes the effect of reinforcement events on the tendency to select actions. Thorndike later modified the law to better account for accumulating data on animal learning, such as differences between the effects of reward and punishment. And the law in its various forms has generated considerable controversy among learning theorists. Despite this, the law of effect in one form or another is widely regarded as a basic principle underlying much behavior. It is the basis of the influential learning theories of Clark Hall and experimental methods of B.F. Skinner. The term reinforcement in the context of animal learning came into use well after Thorndike's expression of the law of effect. To the best of our knowledge, first appearing in the context in the 1927 English translation of Pavlov's monograph on conditional reflexes, reinforcement is the strengthening of a pattern of behavior as a result of an animal receiving a stimulus, a reinforcer, in a... Okay, we can kind of skip that. The idea of implementing trial and error learning, because everyone knows Pavlov and those dogs and their saliva. appeared among the earliest thoughts about the probability of artificial intelligence. In a 1948 report, Alan Turing described a design for a pleasure-pain system that worked along the lines of the law of effect. When a configuration is reached for which the action is undetermined, a random choice for the missing data is made, and the appropriate entry is made in the description, tentatively, and is applied. When a pain stimulus occurs, all tentative entries are cancelled, and when a pleasure stimulus occurs, they're all made permanent. In 1952, Claude Shannon demonstrated a maze-running mouse named Theseus that used trial and error to find its way to a goal location in the maze, with the maze itself remembering the successful direction via magnets and relays under its floor. Other early computational investigations of trial and error learning were those of Minsky and of Farley and Clark. Both in 1954, in his PhD dissertation, Minsky discussed computational models of reinforcement learning. Minsky. Is this the Minsky we're talking? Probably. He's constructed an analog machine composed of components he called SNARCs, stochastic neural analog reinforcement calculators. Farley and Clark described another neural network learning machine designed to learn by trial and error. In the 1960s, the terms reinforcement learning were used in the engineering literature for the first time. Particularly influential was Minsky's paper Steps Toward Artificial Intelligence in 1961, which discussed several issues relevant to reinforcement learning, including what he called the credit assignment problem. How do you distribute credit for success among the many decisions that may have been involved in producing it? All of the methods we discuss in this book are in a sense directed toward solving this problem. The interests of Farley and Clark shifted from trial and error learning to generalization and pattern recognition. That is, from reinforcement learning to supervised learning, this began a pattern to confusion about the relationship between these types of learning. Many researchers seemed to believe that they were studying reinforcement learning when they were actually studying supervised learning. For example, neural network pioneers such as Rosenblatt and Withrow and Hoff were clearly motivated by reinforcement learning. They used the language of rewards and punishments by the systems they studied were supervised learning systems suitable for pattern recognition and perceptual learning. Even today, some researchers and textbooks minimize or blur the distinction between these types of learning. For example, some neural network textbooks have used the term trial and error to describe networks that learn from training examples. This is an understandable confusion because these networks use error information to update connection weights. But this substantially misses the essential selectional character of trial and error learning. Partly as a result of these confusions, research into genuine trial and error learning became rare in the 1960s and 1970s. In the next few paragraphs, we discuss some of the exceptions and partial exceptions to this trend. One of these was the work by a New Zealand researcher named John Andre. Andre developed a system called Stella that learned by trial and error in interaction with its environment. This system included an internal model of the world and later an internal monologue to deal with problems of hidden state. Andre's later work, 1977, placed more emphasis on learning from a teacher, but it still included trial and error. Unfortunately, his pioneering research was not well known and did not greatly impact subsequent reinforcement learning research. Alright. So big way to design a reinforcement learning system is how to actually reward it. You know? So that was a big part of it. Let's just go through the other points that we had. So we started with saying have a matrix that has value for rewards regarding the time. We can start having values in the matrix randomly. And probably have rewards that are not changing anymore. We can have the reward changing based on the position and time. A rate of learning. Why do we need a rate of learning? We can have a rate of learning for introducing limits to different sections of learning. We need to learn a value function. Yeah, that makes sense. Oh, what was that? Delayed effects of a choice. Generalized from its experience. You need to probably choose down on what this means. Play moves from past experiences. Model free creates model methods. All that. These are pretty good in my opinion. Yeah, that's good enough for today for reinforcement learning, but I try to at least have the code a little bit more ready, and we need to have a system of just keeping track of everything that we are doing, and maybe recording it helps, hopefully. What else? And then try different things and see what works. And then also read the books to know like what has already worked. But not cheating. You know. That's good, probably. Yeah, we're just gonna cut this short right now. Thank you for watching this, and as you can see, we've read only 20 pages of the 300 pages textbook, so it's gonna take probably a month till we finish this. So we need to have patience for that.